In this section, we want to talk about diagonal, triangular, and symmetric matrices. For the bulk of the discussion here, right up until the very last thing, we will assume that the matrices we're talking about are square. So until otherwise stated, all matrices are square. Now, definitions here. A diagonal matrix is a matrix with all entries off the diagonal equal to 0. An upper triangular matrix is a matrix with all entries below the diagonal equal to 0. And a lower triangular matrix is a matrix with all entries above the diagonal matrix equal to 0. Sometimes the definitions here seem backwards, where upper talks about below and lower talks about above. But here's some examples, and we'll see why. I'm going to zoom in a little bit here. So this matrix right here, the 3 by 3, the main diagonal here has some numbers on it. And, well, the others have numbers too, but the numbers are all zeros when you're not on the diagonal. Okay? That is a diagonal matrix. Okay? This right here is what I would call an upper triangular matrix, because everything below, there's 3 entries below the diagonal, and they're all zeros. Above the diagonal could be anything, and on the diagonal could be anything, including, it's possible to have a 0 on the diagonal as well. Likewise here, I could have had some zeros and it would still be a diagonal matrix, as long as off the diagonal are zeros. Here, as long as below the diagonal are zeros, it's an upper triangular. This is lower triangular because everything above the diagonal, these 3 entries, are 0. Actually, I should point out that a diagonal matrix is actually both upper triangular and lower triangular. Right? Satisfies the definition, so it is. Now we're going to look at, first of all, some properties of diagonal matrices, and then we'll move on to the other ones. So let's look at diagonal matrices. In particular, look at what happens when you multiply by a diagonal matrix. So I have the 3 by 3 here times this other. This is a diagonal matrix, and this is just a random matrix. You might say it doesn't look very random with the 1, 2, 3, 4, 5, 6, 7, 8, 9, but randomly selected numbers could possibly come out like that. So there. But take a look at what happens when you multiply. Generally, when I think of multiplication, I think of taking columns here and then multiplying it by the first row, second row, third row to end up with the first column. Then you take the second column to generate the second column. Now, some people actually think differently, where they take this first row and they multiply it by the 3 columns to generate the first row of the result. And in particular, if you do it that way, taking this first row, multiplying it down here, you'd get 2 plus 0 plus 0. I'm working my way across that. So 2 plus 0 plus 0, that's 2 right here. And then you'd have this row times that column, 4 plus 0 plus 0, so there's a 4 there. And then 3 plus 0 plus 0, so there's a 6 there. The net result was that first row, 1, 2, 3, got multiplied by the 2. Then if I focus on the second row here, and do the same thing, so 0 plus 12 plus 0, you put a 12 right there. 0 plus 5 plus 0, you put a 15. Sorry, 0 plus 3 times 5, which is 15. 0, 15, 0. And then lastly, the third column, 0, 18, 0. Put an 18 right there. And what happens is this row here got multiplied by 3. That's 3 right there. And lastly, you'd find that the third row gets multiplied by that 4. Multiplying by a diagonal matrix on the left has the effect of multiplying each row in this other matrix by the corresponding entries on the diagonal. So the first row gets multiplied by the first entry in the diagonal, the second row gets multiplied by the second entry in the diagonal, and so on. Okay. On the other hand, if we multiply on the right, put the diagonal matrix on the right, then this one I see the way I usually think of it. So take this first column, 2, 0, 0, you get 2 plus 0 plus 0, that's the 2. Then 8 plus 0 plus 0, that's that 8. 14 plus 0 plus 0, that's that 14. And what happened was this column of 1, 4, 7 got multiplied by that 2 to 8, 14. And then likewise, you move over to the second column. So 0 plus 6 plus 0, there's a 6 right there. 0 plus 15 plus 0, there's your 15. 0 plus 24 plus 0, and you get the 24 right there. And that second column got multiplied by that 3. Right? So anyway, multiplying by a diagonal matrix on the left multiplies the rows by the corresponding diagonal entries, multiplying by a diagonal matrix on the right, multiplies the columns by the diagonal entries. Now there's a question of when is a diagonal matrix invertible? Well, remember what it means to be invertible. To be invertible, you need to be able to find a matrix when you multiply it by the given one, gives you this identity matrix. So this is a 3 by 3. Of course, we should be doing this for any n by n, but the idea is this. I need to come up with a matrix here that's going to multiply but end up being 1, 0, 0, 0, 1, 0, and so on. Well, the thing is, I just figured out that multiplying by a diagonal matrix just multiplies the rows here. So I need a row that when I multiply it by d1 is going to be 1, 0, 0. Well, certainly, if 0 and 0 have to be multiplied to end up with 0 and 0. But in order to take this d1 and multiply it by something to end up being 1, it's got to be the 1 over d1. Likewise, in the next row, this has got to be 0 and 0, so that when you multiply them by d2, give you those two zeros, this one and that one. But to get the 1 here in the middle, I'm going to have a 1 over d2. Whoops. And lastly, they got to have a 0 and 0 here. No, because this d3 is going to be multiplied by all three of those things. But to get a 0 and 0, I need those two zeros. And then to get that 1, I need 1 over d3. Okay. So it's easy enough to see what this matrix should be. Question is, does that always exist? And the answer is yes, if d1, d2, and d3 are all non-zero. So a diagonal matrix is invertible if and only if it doesn't have any zeros on the diagonal. Right? If you had a zero over here, then one of these things wouldn't be possible, and you wouldn't have an inverse. Okay. Now, let's look at triangular matrices. Triangular matrices, I'm going to call UT and LT. UT is upper triangular, that's with zeros below the diagonal, and LT is lower triangular, that's with zeros above the diagonal. Right? All zeros above the diagonal. Not that all of the zeros in the matrices are above the diagonal, but everything above the diagonal is 0. So here we go. Here's a theorem. And these I'm really not going to prove. I think they're pretty evident. But the transpose of a UT is an LT. Upper triangular, if you take the transpose, you get a lower triangular. Remember, rows and columns get swapped. If I look back up at my examples up here, where's my, here's an upper triangular. If I take the transpose, essentially flip that over the diagonal, then all the zeros that are up above the diagonal end up below, and so that this is a lower triangular matrix, the transpose would be upper triangular. Okay. So that's not too surprising and too hard to believe, but yes, the transpose of an upper triangular is lower triangular, the transpose of a lower triangular matrix is upper triangular. A little less obvious, the product of two lower triangular matrices is lower triangular, and the product of two upper triangular matrices is upper triangular. Other things here, a triangular matrix is invertible if and only if all of its diagonal entries are non-zero. This is what we argued for a diagonal matrix, but it's also true about a triangular matrix. As long as you have no zeros on the diagonal, then either upper triangular or lower triangular, it will be invertible. As soon as you have a zero on the diagonal, then it's not invertible. Okay? And in the case that you have an invertible triangular matrix, the inverse of an invertible lower triangular matrix is lower triangular, and the inverse of an upper triangular matrix is upper triangular. Okay? Now I'm going to just give you a suggestion of proof for part B. The book actually walks through it a little more, but I'm going to just see this in terms of just a 3 by 3 case. They prove it and more generally. But the idea here is if I've got, the product of two lower triangular matrices I want to show is lower triangular. Okay, so here's one lower triangular matrix, here's another one. Now, when I look to see whether this is lower triangular, I really just have to look at the entries below the diagonal and say, hey, are those all 0? If those are all 0, then I don't care what these are. This is lower triangular. So I'm color coding here. Let me zoom in a little bit. This entry right here in the second row, first column, I'm going to take the second row here times the first column. And notice what happens. I've got 0 times G plus D times 0 plus E times 0. So I'm getting a 0 out of this first one times the G, and then I'm getting zeros out of the second one times these other two. When I add them all up, I add up with 0. Right? There's just enough zeros to make that entry equal to 0. Likewise, this row, this entry, third row, first column, I'm taking the third row here and the first column there and getting 0 plus 0 plus 0. That also is a 0. And then lastly here, the third row, second column. So take the third row times the second column. I've got 0 plus 0 plus 0. There's just enough zeros from either one side or the other to make every one of the products in my sum here, 0 times h, 0 times j, f times 0, every one of those products has a 0 in it, so then when I add them all up, I end up with a 0. Okay. So anyway, there is the idea behind how you prove that two lower triangular matrices is lower triangular. You should do it in more general, and the book does, but anyway, there's the idea. I'm going to cut this video off at this point, and I will talk about symmetric matrices in the next video.